Okay, so we are on chapter 15. That's not 14 anymore. That's good. All right, chapter 15. And in chapter 15, we started talking about a new type of sort of equilibrium, and that is the KSP, which is the solubility product. And as we talked about, KSP really is sort of the equilibrium constant for things that are typically insoluble and make a solid. So kind of from like your solubility rules, things that normally when you put them together, you would expect a precipitate or a solid to form. So remember that even though solubility rules do say that you will see a solid and a solid forms, it actually will still be soluble in some sense. So even things that are insoluble have some degree of solubility, even if it's super small. And that does set up an equilibrium. So popular solid we all seen over the years, silver chloride, a kind of white solid. Even though based on solubility rules, again, it tells us obviously when silver and chloride come together, we would expect a precipitate to form. It will still set up an equilibrium in solution and will break apart a little bit into its ions of silver and chloride. And that does set up the equilibrium, which is where we get our KSP expression from, which in this case would be our silver concentration and our chloride concentration. And that is usually the case for sort of KSP expressions. It really is usually just the products, as these reactions are always sort of written kind of solid on the left there and aqueous ions on the right. So as we normally do, we don't include anything that's solid, liquid, and such in our equilibrium constant expression. So we don't do that here. So again, usually it's just the products. We do still do everything else like normal. So if there are some coefficients, you do need to take those as the exponents and all that good stuff as well. So when we talk about KSP, there's kind of two types of problems typically that you're given, but really both problems, is really a good idea to maybe do an ice table. And when we do an ice table, it is a little bit different in the sense that because the side is usually solids, we usually don't have anything obviously on our left-hand side here because we're not going to be really concerned about that, as that is obviously a solid. We do start with zeros. And as we talked about last time, oftentimes with these type of tables, we do use sort of a different sort of letter for the change. You really could still use X if you like, but a lot of times people will use S in this case. So this would be plus S and plus S. Again, if we did have some type of coefficients there, you would need to include that with it as well. And we come down here, this like kind of a normal calculation would go into our KSP expression, and we would have obviously the number for the KSP, and we can solve for S. When we do solve for S, S is the molar solubility. So that is the molar solubility. It is basically the molarity, moles per liter. And that is one way that we sort of express solubility is through molar solubility. We also can express solubility through grams per liter, which is a common sort of way of expressing it. And as we talked about last time, kind of going from molarity to grams per liter. Again, the thing that sort of ties that together is the molar mass. And again, you can get that obviously from the periodic table, grams per mole. Allows you really to go either way, either from moles per liter to grams per liter or grams per liter back to moles per liter. Now, because these guys are for things that are typically insoluble, we typically do see a very small value uh, for KSP, and they're typically very small. And because it's still an equilibrium expression, as we talked about before, if you have a small value of K, you would mainly expect reactants to be present at equilibrium, which is what we see here, which is the insoluble solid. In fact, we did this calculation, I think, and we saw something like you could dissolve it was like 0.002 grams of silver chloride in 1,000 milliliters of water, which is pretty much nothing, right? Getting dissolved, and it typically is going to be insoluble. So, um, key things that people kind of mess up on, as I mentioned last time, is again, kind of like they do like a 3S and then forget, like, do I still need a kind of a qubit as well, or they qubit and don't do the 3S part of it and stuff like that. And just calculation wise, like one of the ones I think we had last time as well. When you got something like this, it is very, very common people just do the letter and again, not the numbers. So make sure that you kind of avoid those things. Any questions on that there? When you do solve for S, it is, as we talked about, really the molar solubility of the entire thing. It may, as in this case, also be the concentration of silver ions in solution and chloride ions in solution as well. So you can put that S back into the end line there at equilibrium line and solve for the ion concentrations as well. All right, so speaking of that here, let's talk a little bit about using KSP values to determine whether or not a certain compound is sort of more soluble than another. And when you look at, say, these three salts here, the silver iodide, the copper 1 iodide, and the calcium sulfate, you can use the actual KSP values to directly compare the solubilities of each of those and decide which one should be more soluble, which one should be less soluble. So if we take a look at each of these sort of equilibriums here, we have our silver iodide that will break apart into a silver ion and an iodide ion. We have our copper 1 that will also break apart here into a copper 1 and an iodide. And lastly here we have calcium sulfate that will break apart into a calcium ion and a sulfate ion in this case. Now, what each of these basically shares in common is how many ions they break apart into. So every one of these sort of salts, when they do break apart in solution, they all break apart into the same number of ions. And because of that, what that really means is the math that you would do for each of these are going to be identical. You basically take the square root of the KSP value for each of them because they each are going to give you basically S squared is equal to the KSP. So you're going to basically have the same calculation that you're going to do for each of them. And that means that you can compare the results of each of those directly as well. So because they actually do break apart into the same number of ions, you can use the KSP value directly to compare. So how do we use the KSP value directly to compare? Well, again, since each of these KSP sort of expressions are this situation, solid on the left, aqueous ions on the right, if we have a small or KSP value, that would mean that we would expect mainly reactants to be present, right? Versus a larger KSP value, which is again just a K value. And with a larger K value, we would expect products to be present, right? So the one with the larger KSP value should have more aqueous ions present. And because it has more aqueous ions present, it should be more soluble than something with a smaller KSP value, which will have less aqueous ions and stay together more and be more insoluble. So you can, in this case, directly compare the KSP values. And if you do look them up, you will see calcium sulfate there I didn't draw my arrow through it there. Calcium sulfate there will have the larger KSP value, and that means that it should be more soluble than the other two. And you could kind of rank them based on solubility. Again, in this case, silver iodide would have the smallest KSP value, and we would expect more reactants present in that case, less ions, and that means it's going to be less soluble and more insoluble than the other two. Questions on that? So as long as you're comparing two things that break apart into the same number of ions, you can directly use the KSP to determine. And that's helpful, for example, if you have things floating around and you want to think about which one may come out of solution or first and which one will stay in solution longer, as you maybe selectively precipitate one thing out versus something else. Now, what happens when you are not comparing things that do not break apart into the same number of ions? So, for example, here we have copper 2 sulfide. And again, when this guy breaks apart, we will get a copper 2 ion and a sulfide ion. We have a little silver sulfide here. And when this guy breaks apart, we will get 2 silver ions here and a sulfide. And we got a little bismuth there, 3 sulfide. And when this guy breaks apart, we will get 2 bismuth there and 3 sulfide. So when looking at these guys here, obviously we have 2 ions. Here, this guy's breaking apart into 3 ions, and this guy's got a lot of them floating around, and there are 5 ions. So in this case, they do not break apart into the same number of ions. So just to illustrate, if we went by the KSP value here that we could find in a book, we do see that the copper 2 sulfide has the largest KSP value, with the bismuth here having the smallest KSP value. And if we ranked them based on solubility and the KSP, we would actually say that, this guy probably should be more soluble. And this guy should be least soluble of the bunch. But when you actually do the calculation, which is actually what you have to do, so you have to do a calculation for each of these salts like we did in the previous examples earlier on in the chapter to figure out the molar solubility of everybody. What you actually see is actually the bismuth that is the most soluble, while we have our copper 2 sulfide is the least soluble. So in this situation, because we have different numbers of ions, you cannot use the KSP directly. Instead, you got to do a calculation. Questions on that? So, same number of ions, good to go with the KSP to compare. Different numbers, you got to just flat out do the calculations for everybody and then compare at that point. Any questions? All right. So let's then talk about one thing that can affect solubility. So earlier, I think I mentioned that when you learn solubility rules and you sort of think about solubility rules, sometimes we think of them as sort of 100% correct in all situations. And that is really not the case. So when you do have certain situations, you may not see, for example, a solid form when you're supposed to based on solubility rules. And there are a few factors that can affect whether or not, for example, you'll see the solid or will not see the solid. And one of those things that can affect solubility is the common ion effect. And the common ion effect, much like what we saw when we were talking about acids and bases, if you remember, if you have a common ion, it basically will keep the weak acid or weak base together. And it's very much the same situation that occurs here. if you again just think about how these KSP sort of reactions are written, we have solid, and on the other side, again, we have aqueous ions here. So obviously, in this case, the only place you could have a common ion is the product side. Those are only sides that have ions. So because you would have a common ion on the product side, our good friend Le Chatelier's principle would say, if I add to the product side, I should see the equilibrium shifts away from it, and it should shift to the solid side here. So we would again see in this situation, because of that equilibrium shift, more solids stay together because of the presence of that common ion. And if we do see the solids stay together more, that's going to decrease the solubility of that compound, right? It's going to basically keep it together and not allow it to break apart. It's kind of the same idea again as we talked about with acid and bases with a common ion. It suppresses the weak acid from ionizing, right, and breaking apart, or the weak base from ionizing and breaking apart as well. So, for example, here, if we take a look at silver bromide, and that's the KSP there for silver bromide, which is 7.7 times 10 to the minus 13 is KSP. And if we look at the solubility here of silver bromide in water, just pure water by itself, we would set up our equilibrium reaction here, our silver bromide breaking apart into our silver ion and our bromide ion here. That obviously is going to give us a KSP expression of silver times bromide. And that's going to equal our KSP of 7.7 times 10 to the minus 13. So if we do our ice table here, we have 0 and 0. This will be plus S and plus S. This is going to give us, when we reach equilibrium, S and S. So we just kind of do an ice table like we talked about previously. We will then put these guys into our KSP expression, and that will basically give us S squared is equal to 7.7 times 10 to the minus 13. I'm going to square root both sides here, and that is going to get us here a S value of minus 13. That's too many zeros to count just early. Let's see here. Let's try that. That's going to give us something like an 8.8 times 10 to the minus 7. This is the molar solubility here of silver bromide. And again, if we use the molar mass of silver bromide, which is 107.9 plus bromine like 7990, and we multiply it by each other there, we get a solubility of grams per liter of what we got there. This number here, I think. How about not too big here, 1.6 times 10 to the minus 4 grams per liter. So basically in water, we could dissolve 0.0002 grams, basically, a very small amount, essentially. First off, any question on that calculation? And obviously this would be our molar solubility here, right? So now what would happen here if we did it not in pure water, but in the presence of 0.001 molar sodium bromide? Let's see if I could just go backwards here. Yeah, that'll work. All right, so if we take a look at what's happening now in part B, we have the sodium bromide present, and the sodium bromide is a salt, which is a strong electrolyte, and it is not going to stay together in solution. It's going to break apart into sodium ions and bromide ions. Now, if we come to our table here, a little silver bromide, and our silver and our bromide here. So initially, again, we have 0 of the silver, but in this particular case, we do have some bromide present, as that's going to be our common ion. And since this sodium bromide is 0.0010, it is a 1-to-1 relationship between the sodium bromide and the Br minus. That means our initial concentration here is going to be 0.001 molar, as that is being supplied by the sodium bromide in this case. The rest of the table will be very similar. We'll go plus S, and again at the end here, we'll go S and 0.001 plus S. Any questions on that there? So again, the sodium bromide here providing that initial concentration. Now, we're going to put it into our expression, which will give us S in this case times 0.001 plus S is equal to our KSP, which was, where's that, 7.7 times 10 to the minus 13. Well, one of the good news here is that is a small value of K, which typically KSP values are. So as we know, whenever we have a small value of K, we can do our favorite thing ever, which is an assume, in this case, S is equal to 0. Much like how we assume X is equal to 0 here, we can't get rid of all the S's. It, in this case, will be whatever S you're going to add to a number, maybe subtract, but most of the time we'll be adding. So it is going to be just that S there that we're going to get rid of. And that will give us S times 0.001 equals 7.7 times 10 to the minus 13. Now all we have to do, again, is divide that 0.001 to the other side. And that's going to give us our molar solubility here of 7.7 times 10 to the minus 10 moles per liter. And we could also multiply that by the molar mass of silver bromide, which is 187.8 grams per mole. 187.8. And that's going to get us here somewhere. Actually, I'll get rid of that there so you can see it. That will get us here. Looks like 1.5 times 10 minus 7, if I counted all the zeros right there, grams per liter. And again, that is our grams per liter. This is obviously our molar solubility here as well. First off, any questions on that calculation? You can check your assumption here. So if you take 7.7 times 10 to the minus 10 and divide it by 0.001, you're good. You're nowhere even near 5%. So I would say in a lot of cases, your assumption should be pretty good on these since the K value is very, very small. Now, when we compare in pure water, and you can compare either one, in pure water, we were able to basically dissolve as I said, 0.0002 grams per 1,000 milliliters of water. With the common ion present, we were able to dissolve like 0.000001 or 2 grams, right? So much, much smaller solubility. So here our solubility decreased a lot. And it decreased because of, again, the presence of this common ion right here. And Le Chatelier's principle shifting the equilibrium to the left and keeping the solid together. So much like we saw with weak acid and weak bases, that common ion basically going to keep everybody together. In the case of solubility, obviously will decrease the solubility of that particular compound. Questions on that there? All right, we'll lay it up there for now.